So now to something different. Okay, so now imagine that you have a surface mix layer, and the thickness of this layer is h. We call it h. That's the thickness. And just imagine that it's 10 meters deep. Okay, and now we're talking about two processes that happen at the same time that can change the salinity of your surface mix layer. Salinity is the salt concentration. Okay, there are two processes. One is called evaporation, which is E, and the other one is precipitation, P. Okay, they processes that can happen at the same time. Evaporation is the removal of fresh water from the oceans. Precipitation is the addition of fresh water through rainfall. Okay, so what matters, what changes the salinity is E minus P. And now I show you a little bit. I know that you're all freaking out because it's a formula, but okay, let's just briefly go through that. It's a formula. Okay, you can see formula. I'll try to illustrate with the mouse here. This is the formula. And the formula has two sides. And in this sense, it means what happens on the right side also happens on the left side. So you have a cause, and the cause is linked to E minus P. Okay, and other things that I'll explain in a second. And you have a response, and the response is shown on the left hand side. And what the response is, it's something called dt, ds dt. This means how will the salinity in the surface mix layer change over time. Okay, if what's on the right hand side is 0, means that the salinity will not change. It will stay the same. If there's a 0 on the right hand side, means there is no rate of change. 0 change. It stays the same. If the evaporation minus precipitation is positive, means that the salinity will increase. Okay, so now there's a little bit more to it, because you can see that the thickness of the surface mix layer is in this formula. And what it means is that if you have a thicker layer, then the rate of change will be smaller, because that salinity change will be distributed over a thicker layer. In addition, it's also the entire right hand side includes S, the salinity. So also the salinity change is proportional to the salinity itself. And this makes sense if you think about fresh water. So you have a glass of fresh water and you let evaporate, and you don't magically create salinity in that. So if there's no salt in it, there will be never any salt created. So you need the salinity to start with, and the rate of change is also proportional to the salinity you start with, or the salinity that you have in your bowl. Evaporation depends on the wind speed and relative humidity of the air. Okay, and these changes and fluxes, and I forgot to mention that, is you always imagine that you have sort of a horizontal area of 1 square meter, and then the vertical scale is given by the depth of the surface mix layer. So in the oceans, there is a very strong correlation between the surface salinity and the evaporation minus precipitation. Okay, and this one is in the shown above my head, where you can see individual curves of precipitation and evaporation from the North Pole to the South Pole, and again you can see the very, very strong signature of the intertropical convergence zone. Okay, you can see that peak, and you in the bottom panel you see evaporation minus precipitation in centimeters per year, and the surface salinity of the ocean. It's an almost 1-to-1, except for polar regions, a 1-to-1 correspondence. Okay, and this is what we call the changes. This is how salinity changes in the surface oceans, except for currents, which can also move salinity anomalies along.